What if I told you that the blueprint for a successful, sustainable future had already been written? Well, it has. And it's all around us, whether you're looking or not. The natural world has been doing chemistry, green chemistry, life-friendly chemistry for billions of years. So the real question is, are we willing to learn from nature? It's no secret that since the start of the Industrial Revolution in the 1760s, we have produced an unfathomable amount of toxic waste. In fact, according to a recent EPA report, over 34.9 million tons of hazardous waste was produced in the United States in just 1 year. And that's only by the large quantity generators. It's only in recent years that we've really started to see the consequences and have begun to turn towards the concept of designing with sustainability in mind. There are efforts being made to clean up the mess, but how will we move forward? And more importantly, can we continue to grow and innovate without continuing to add to the problem? Don't get me wrong, recycling plastic bottles is a great initiative, but could you imagine the impact if we stopped producing them altogether? Biomimicry is a quickly growing field. Simply put, it involves the investigation of well-adept organisms and the translation of their exceptional adaptations into a usable design principle for the resolution of modern design challenges. There's some classic examples of biomimicry that you might recognize. The highly efficient wind turbines by whale power emulate the flipper tubercles of the humpback whale, which helps to reduce drag and increase lift. The Japanese Shinkansen bullet train emulates the beak geometry of the kingfisher, a design shift that helps to reduce noise and eliminate the tunnel booms that were problematic in previous design iterations. The biomimicry design also allowed the train to travel 10% faster using 15% less electricity. And Velcro, a classic example of biomimicry, initiated by a Swiss engineer and inventor who noticed the little burrs that stuck to his dog's fur after a hike. The unique fastening mechanism of the microscopic hooks, which helps plants to transport seeds, was emulated into what is now known as hook and loop technology and found in textiles across the world. So what do all of these examples have in common? Each of these is an example of form-based emulation. In the most common examples of biomimicry, the adaptation of a larger shape or form is employed to provide the characteristics needed for design improvement. If you were to Google examples of biomimicry, most of what you would come across are these sort of mesoscale examples. Now, there are some instances of biomimicry in business management or closed circle infrastructure at the macro scale. But finding examples of biomimicry on the micro scale is difficult to do. And it's disappointing because if you think about it, every design boils down to chemistry. These form, process, and ecosystem-based emulations are wonderful. But what are they being made out of? And how are they being produced? These questions apply to every design, regardless of industry. So why aren't there more examples of biomimicry and chemistry integrated design? I don't actually have the answer. I suspect that it might have to do with the assumption that chemistry is hard. Most people don't really understand the scientific language. And Using the same materials and methods to produce a prettier design is a whole lot easier than it is to create something entirely new from the ground up. Regardless of the reasoning, though, my point is that there ought to be a biochemist at every design table to help bridge that gap. We need scientists and their research to be part of the design process. In biomimicry, there are a set of life's principles, a sort of benchmark of sustainable attributes by which to design while creating conditions conducive to life. One of these principles is to use life-friendly chemistry, but it is perhaps the least understood and the most often avoided principle in biomimicry. So if we know that we need biomimicry innovation at the chemistry level in nearly every design instance, but we are also aware that most companies have just begun to include biomimicry professionals on their design teams, and the majority of those folks are not experienced chemists, then what are we supposed to do? How do we get true biomimicry innovation on the micro scale? In a recent webinar with John Warner, he posed the question, how do we get better at inventing? And my answer is quite simple. Know when to ask for help. Rather than avoiding the areas of a design that seem too difficult or too intricate, make collaboration the norm. I had a high school science teacher many years ago, and he always used to say, you don't know what you don't know. But it's true. Identifying the areas of a product or a process that could really benefit from biomimicry thinking or green chemistry integration isn't an easy thing to do, especially if you have no idea what you're looking for. So let's bridge the gap between science and business. Make collaboration the expectation, and don't hesitate to call on the experts. Whether you're working to store energy or looking for ways to transport resources, maybe you need to maintain moisture under extreme circumstances, whatever it might be, bring a biochemist in to work hand in hand with a biomimicry professional and explore nature's examples for potentially revolutionary improvements. So what happens when we succeed? Now, they're not always easy to find, and they certainly aren't making the headline news these days, but there are some absolutely extraordinary examples of biomimicry in chemistry. And those with sustainability in mind, putting the green chemistry principles into action, are at the top of my list. Take Grow oyster reefs, for example. Their patented Grow concrete is specifically designed to emulate the natural oyster shell. In addition to being naturally derived, Grow concrete provides early stage nutrition and attracts oyster embryos and other species to help nurture reef biodiversity and foster restoration. The result is cleaner water, shoreline retention and surge protection, as well as carbon sequestration potential. Spintex is another fascinating company. Inspired to address the fast fashion industry, their team has emulated not only a spider's silk, but the biochemical process by which it is naturally formed, mimicking the shear flow mechanism of stretching liquid protein into biodegradable fibers. The process is done at room temperature, without any harsh chemicals, and leaves water as the only byproduct. Not to mention that the process is 1,000 times more efficient than that compared to similar plastic fibers. The final product is a high-performance fiber with strength and toughness while remaining lightweight. The applications go far beyond fashion, and the company has started to look into the automotive, aerospace, and biocompatible medical textiles industries. Another company, Sudoc, has taken to emulating the way enzymes, like those in our livers, oxidize pathogens and toxic chemicals. Their TAMIL catalyst emulates the way the peroxidase enzyme works, but it has a modified form which makes it stable outside of the body. The implications are broad, capable of replacing or eliminating toxic chemicals that are typically found in pesticides, wastewater and pharmaceutical waste management, as well as household cleaners and so much more. And the best part is that the TAMIL catalyst is biodegradable, so it breaks down after its job is done. We have the answers to our challenges right in front of us. We have proof of successful adaptations for sustainability and longevity at our fingertips. The next step is to bring the experts into the research and development phase, to make collaboration the norm, to have chemists, biomimics, toxicologists, and biologists working hand in hand to share their research with those who are designing, marketing, and producing new technologies. We know what to do. So let's make change happen with innovation through emulation. Thank you.